Okay, hello everybody. Thanks for the introduction. And as we said, we will have a look on sensor selection. So a little bit of situation in between hardware issues and machine learning issues in a daily life setup. So let's dive right into it. Where do we come from? We started with dementia care and designed a Backplaster and Rackplaster sensor platform that is fixed here between the shoulders and provides an accelerometer, fall detection, then localization techniques in case that the patient gets lost, and finally a communication platform. So in order to provide the position data and the alarms to the service personnel, to the treating physician perhaps, and to the families of the patient. And what we see here is first a concept picture during the project time, and in the beginning of this year, this product was commercialized and is now sold in Germany by Moyocare. So that was quite fine, but we didn't stop here and now thought, well, we have a communication platform, we have already different sensors. Why don't we extend this platform to treat other clinical diseases? So we added, or are currently adding, different sensors, so mainly the ECG. Here, a microphone for heart and lung sounds, and activity, which is the focus today. Now, with the different sensors, you have different applications, of course. So ECG for cardiac arrhythmia, heart and lung sounds for valve insufficiencies, respiratory diseases. But the big benefit comes if you fuse the data. For example, if you go for ECG sensing and heart sounds, you can compare the electrical, the information transmission, the ECG, and the mechanic reaction, so the electromechanic coupling in essence. And if you use the activity, you can relate the analysis of breathing or heart frequency to the context of your sensors or to the physical load that they are doing. So, because ECG or breathing is more informative if you know if the patient is at rest, for example, or if he's doing heavy sports and therefore heart rate increases. Now, what we use the activity for is as context information for our sensor analysis. Okay, now, what are the requirements if we design such an activity classification system? Of course, it has to be accurate in terms of therapy or diagnosis, so we need a high classification accuracy of our sensor plus the algorithms, therefore. And then the second big challenge is the integrability into daily life. So we need a system that is small size. So for example, like this Backplaster for the between the shoulders has to be robust against different disturbances and has a long battery life. Now the small size, at least for the activity sensors, that's not the big problem. Also the robustness, that's okay. But the big challenges are here the trade-off between high classification accuracy and long battery life. And that's the topic for today. How do we get low power consumption and at the same time a high classification accuracy? How did we analyze that or approach this question? First of all, we provided a quite simple sensor platform based on Arduino Micro. So it includes an 80 mega 32. Put on the classical sensors that are used for activity capture, so an accelerometer, and gyroscope, and also a sensor for barometric pressures intended to differentiate between different height changes. And finally, a micro SD board for storing the data and then doing all the classification analysis offline to be able to compare different algorithms, different parameter setups, with always the same data. In the long term, of course, we would try to get the data analysis on board, but for this purpose here, we just stored the data and did the offline analysis. Right, then we performed the study protocol and mainly focused on different aspects of walking. Now, jogging is here for completeness, but the typical sport or the maximum of sport that patients with heart or lung diseases are typical, walking the stairs. So that's what we put the focus on, so walking the flat, upstairs, downstairs, and standing and jogging. The study protocol was for each of the training data recording and for the test data recording about 20 to 30 minutes. And we performed that with a study population of 20 probants, nearly half male, female. And you see 24 years old, plus minus, were mostly students of our institute. Right, from the sensors that we get from the sensor platform, we get accelerometer and gyroscope, 3 axes each, plus the absolute value, and one scalar value from the barometer. That makes 9 measurement variables in total. And for each of these variables, we had 20 time space variables, 9 frequency space variables. They are given in the papers. I don't list them here. So in total, we get the 261 features in total, and these are provided to the optimization procedure, where we used the k-nearest neighbor and had several pre-parameters for optimization. So set up for the moving window that we applied, normalization of the data, tried out different feature selection methods, and for the k-nearest neighbors approach, we have different possibilities concerning the metric and the degree. And did the standard approach, so optimized with respect to the FA1 score on the training data, and then evaluated the whole thing with the test data that we recorded. And finally, we compute also the computation time, so the time for the classification. So we didn't look at optimization procedure, but the time consumed that is critical for real-time applications. And normalize this time for the optimal parameters. Okay, let's have a look on the power consumption first. And what you see is that you get quite a hierarchy of the sensors. So gyroscope consumes nearly 12 milliwatts. The accelerometer nearly 1 order of magnitude lower, and the barometer is nearly negligible concerning the power consumption. So power is always dominated by the topmost sensor that we use, and you see here, if you can get rid of the gyroscope, we can get considerably better in power consumption. Okay, we established optimization results for the full sensor set, for the optimal setup, and got here, quite good results, always above 90% concerning sensitivity, precision, and F1 score. Now the main finding is, so if we now go for different sensor combinations, we get again the full sensor set here, and indeed it gets the best F1 score with a 95.7%, but also highest power consumption and highest computation time. On the other side of the spectrum, we get the barometric pressure with a very low F1 score, but with the best, of course, power consumption. So somewhere in between must be the trade-off. And so what we find is that if you take, remember our hierarchy of sensors, the accelerometer and the barometric pressure here in this column, you get considerably good F1 score, so only 0.7% lower than the F1 score for the full sensor set, but a power reduction by 88% and also computation time reduction by 45%. So that's not bad. And with a considerably good classification result. Okay, We have a short, little bit of time left to look into the details. So look in the full sensor set once again, and we have here on the diagonal the optimal results are always quite high in the 90%. Now if we go for the accelerometer only, we see that we have a considerably reduced performance concerning the types of walking. So we have here walking in flat, walking upstairs, walking downstairs. So that's a problem that the accelerometer has. Barometer, that's very good to detect height changes. So it works quite well here for detecting walking upstairs and walking downstairs. But anything that doesn't involve any height changes, yeah, well, it's quite confused. And now if we put those two together, the accelerometer and the barometer, well, we get the quite well performance that is comparable to the results of the optimal to the full sensor set. Okay. I skipped that for unknown activities. We also looked at what happens if we apply our sensor for activities that weren't planned at first. So for using elevators, sitting and taking the bike. So that's quite well. So using the elevator and sitting are both classified as as standing, so kind of rest in both cases. But what is more problematic and has different classifications are riding the bike. Okay, and with that, I come to the conclusion. I just showed that we can find by clever selection of the sensors that we use, we can nearly match the classification results of the optimal of the full sensor set by simultaneously reducing the power consumption by 88% and also the computation time by nearly halving it. Now, the next steps that we would do are to test other machine learning approaches apart from the KNN, then would have a closer look on the activities that we take, so taking the bike for example, and later on apply the intended data fusion approach to compare activity classification and out and lung cells. Okay, and that's all. Thanks for the attention, and yeah, hope for questions.
Questions?